Alright, so today we're gonna continue our lecture regarding the engineering materials. Okay, so you should be able to see this one, yeah, yesterday. So I think I'll just give a little bit of review from yesterday. And this, okay, so this is so yesterday we talked about the importance of engineering materials as well as material selection. For example, of course, if you have a very if you have ill-designed piping or piping tank something, so it can cause catastrophic failure of a gas pipe that undergone a thinning into erosion and corrosion, for example, in this case. Okay, and and also with the material selection, we can also select which material that is suitable for the application. Okay, again, because the economic consideration, safety, aesthetically seen, yeah, and also there are so many constraints that we have to think, and then that's gonna be resulted in a good material selection. Yesterday, we also see that the material cost is actually quite significant, and it doesn't change unless the material itself is changed. Okay, and this one is the famous Titanic one, and also this one, yeah. So this is actually the famous material failure, the Haville Comet, where it was first commercially airline designed to fly higher, but then there is a series of accidents, yeah, and 3 of them breaking up in the middle of the air. It is actually because of the metal fatigue. So metal fatigue or kegagalan lelah, yeah, that's also one a very quite large phenomenon that we can see it all the time, where the metal fails due to prolonged cyclic stress. So an example of metal fatigue is a bridge, yeah, or a building which is suddenly collapsed after a few years, and then there is no sign before that one, and then this that is called a metal fatigue. In this case, the jet airliner, they have compression and decompression because of the different of the difference of the pressure, I think, yeah, between inside the cabin, also from outside, and then some ill design, so then there would be a metal fatigue. Okay, so that is the yesterday, just for the introduction. So now today we're gonna continue our lecture to about start from the beginning, which is from the crystal structure, or maybe from the atomic level, yeah. Right. Okay. Oh wait. So let me try to see. Okay. So this is the crystal structure. Yeah. So the hierarchy material of structure, again, we start with atomic structure, how protons and neutron and electron arrange, and then once each atom structure, and then there is a crystalline structure or inter-atomic structure, and then how different atoms arrange to form molecules, crystal or macromolecule or polymer, for example. Okay, And then from the crystal structure, then we move on to the larger scale, which is a microstructure, where the whole molecule, crystals, and macromolecule are arranged to form features. Okay, so observable by microscopy, mainly porosity, phase distribution, and defect. Okay, and then the last one is the macrostructure for featuring solid structure observable by the naked eye, often combined with the effect of material processing. Okay, so this is a very review. I think you should also get it, yeah, from the Bohr atomic electron. I will not go into details. So there are two atomic models. If you remember, Bohr models and wave mechanical models. While the Bohr model assumes that electron should be particle orbiting the nucleus in the discrete way, while the wave mechanics consider them to be wave-like and treat electron position in terms of probability distribution. Okay, and then we know also there's a numbers of electrons, so I think I'm just gonna skip this one. And you should remember as well from your chemistry about the comparison of Bohr and wave mechanical atoms, yeah. This is just to refresh our knowledge. And then yeah, we remember in high school how to calculate the subshell 1s, 2s, 2p, and so on, yeah. So I'll just skip this one. And also this is the electron orbitals, and also the electron energy that's defined by Bohr and wave mechanics. Okay, if you think you need to just refresh this one, I think you can read the book or check again your chemistry basics, but it won't be included, of course, in the exam. But this is just to refresh your knowledge about the atomic knowledge. Okay, so what we can learn from this electron configuration, we know that the electron configuration, usually from the outer one, this one will define where it belongs, yeah, in the system periodic, right, in the periodic table. For example, you understand that for magnesium, for example, so this is there is a 3s2, so it is belong to the alkali earth, ya, earth alkali 2A, golongan 2A. Or the sodium, this is a very famous sodium, should be belong to the periodic table. Okay, so of course you also familiar with this periodic table. So what we know, of course, from high school, that this one, the group 1A and 2A that can be ionized become cation, yeah, while the for example the 7A or 6A that can be also ionized as a negative, or the anions. Okay, and the bond between the positive and the negative is called the ionic bond. Oops. Yeah, but that's about ionic bond. So ceramic is actually based on ionic bonds. So then you will see, for example, a compound in ceramic, compound in ceramic, for example, MgO. So the Mg comes from so the Mg maybe comes from or this one, yeah, the MgO, and then the Mg, and also the anion came from the O. So then we can get MgO, for example. Okay, so this is a ceramic. Okay, and then metals. Where's metal? So metals is around this area, this one, yeah, the area. So around group B, from 3B, 4B, 6B, 7B, and so on. And if you remember, this is belong to metal. So you will have, we call it metal bond. Yeah, and this one is actually the ceramic is actually based on ionic bond. Okay, now for polymer, how about polymer? So polymer is about hydrocarbon between C, O, F, and so on. Yeah, so this one, it is actually based on covalent bond. Yeah, this is a polymer. Okay, so this is give you an idea. So where the materials are. Okay, so so the metallic element is categorized as electropositive, which they can give up their valence electron to become cation, yeah, or conversely, the element on the right side of the table are electronegative, which they can accept electrons to become anions. Okay, so this is also the electronegativity of the scale, yeah, the elements. And this is also the bonding forces between two atoms, yeah, and there's some model for that one. Okay, now the intra-atomic bond. So the intra-atomic bond is categorized as a first a very primary one. So there is a primary one. This is relatively strong. For example, between metal and metal, yeah, atomic metal and atomic metal, it is a very strong bond. Okay, so then that's why if you have this one, aluminum or iron, for example, they're very strong. Why? Because the bond between those atoms is relatively strong. Okay, the second one is the secondary or relatively weak bond. For example, the relatively weak bond is sometimes maybe, for example, van der Waals bond between hydrocarbon, maybe in polymer. So the impact of the structure, the polymer is relatively soft. Yeah, I have, for example, I have this one. Yeah, the plastic bag. I can easily tear it up. Yeah, that's because it is quite relatively bond and based on the atomic structure between the polymers. Okay, so the primary bonds is ionic, covalent, and metallic bond. They are quite they're very strong. So an example of ionic and covalent is in the ceramic, yeah. That's why ceramic or concrete, beton, yeah, your walls or glass, for example, that's relatively strong because they have the primary bonds. So the properties again will affect with based on the structure. And the secondary bonds, van der Waals, like in the polymer or hydrogen bonds. Okay, but in reality, the difference bonding is not clear cut. So there are mix and match. There's a mixed bonding behavior. Yeah. So, but we can calculate, we can measure how many percent it is, for example, ionic bonding, how many percent it is covalent bonding. Okay. So this one, yeah. So the ionic bond is from electrically charged ions, which is formed by the transfer of valence electron from the micropositive atom to a more electronegative atom. And the attractive between cation there is the force, yeah. And ionic bonds are non-directional. The second one is the covalent bond. An example covalent bond is sharing between electrons. Yeah, for example, silica. For example, silica or SeO2. Yeah, in the silica, the silica has six atoms from the outer one, and each it is shared with the yeah, two of them is shared with the oxygen. So and then it makes covalent bonding. And then metallic bond, the valence of electron is not tied to a specific nuclei, so they move freely and uniformly dispersed around the metal ion core. Okay, so yeah, so why we have to learn about these bonds? Because these bonds actually define the type of material that we're looking at. And after this, I think I can show you videos from Coursera that I have put into the EduNext, but we can have a look together. Okay. Okay, so for example, this is the formation of ionic bonds. A very famous example of ceramic, contoh keramik, is a sodium chloride. Garam dapur, ya, sodium chloride, salt, is actually a type of ceramic. Even you say, Bu, that is salt, garam, yeah, but this on the category for material, it is also called as a ceramic, because in the it has the ionic bonds, and then they attract the bonding, yeah, between the positive and negative. Okay, and then this one again is about the covalent bond. If you remember, for example, this is for example the covalent bond in methane. Yeah, this one, and in the methane you can have a look here that this one there's a bonding between the carbon and also the hydrogen, and they share the electron together. Okay. And then this one is the illustration of metallic bonding. So in metallic bonding, the atom is the electron is moving freely everywhere. Okay, so because the electron can move freely around this positive or around the atom, so the metallic bonding has a very strong bonding. Yeah, that's why the metal relatively has a very strong bonding that result in a high strength. Okay, and this one is the van der Waals. So the van der Waals, this is just the description. So the van der Waals, for example, just between two different two atoms together, but there is a secondary bonding. Okay, so so in a sense, in reality we have mixed bonding. Yeah, the mixed bonding, the one that we see in the reality, usually there are the covalent ionic, there is a covalent metallic, there is a metallic ion, and also a mixed bond. For example, we can see this one, this pyramid. Let's say we have the metallic bonding, which is the material is metals. Okay, and then we have the ionic bonding. Okay, and then we have molecular solids or van der Waals bonding. Okay, so and also we have covalent bonding. So usually the polymers, most of polymers have covalent bonding. Okay, this one, and this is molecular solids, and then the ceramic is actually between this area. Yeah, the ceramic between ionic bonding and also the covalent bonding, while the very close to covalent bonding is is called the semiconductor. Okay, and between ionic and metal, they can also group together as a compound, and the compound is called intermetallic. Okay, so yeah, so before we move to next part, or before you ask questions, so I would like to maybe just let's share some videos. Yeah, just give me a second. So the first video is to the professors tells you about the structure leads to properties. So let's have a look. Okay, so
what we've just seen in defining these 6 categories of engineering materials based on structural and electronic considerations is that in each case, either through an atomic level structural issue, the bonding between individual atoms, or in the case of the chairs, the microscopic architecture of the fiber reinforced composite, we see an underlying principle that is going to be a mantra for material science throughout these 10 things, and that is structure leads to properties. That's the underlying concept that informs all of material science, really. A structural issue, either on the atomic or microscopic level, that leads to our understanding of the nature of the material on the macroscopic or engineering level. So we're now going to look at a short, detailed lecture in which I discuss how the bonding curves, both the bonding force and bonding energy curves that we recall from freshman chemistry, lead us to an understanding of one of the most important of the mechanical properties of engineering materials. And we'll look specifically at the case of the elastic modulus or stiffness of the material. We'll come back to this in more detail in a later segment in another thing. But for now, we want to use this short lecture as our first formal example of how structure leads to properties. So now let's step back and talk in a little more detail about some concepts that we raised early on in our discussion of the stress-strain curve. And this particular sketch is one that I feel is, quite frankly, one of the most important in the course, and so I want to really highlight that and emphasize that this is one of the really seminal examples of this point we've made from the beginning in this course on engineered materials, that that fundamental underlying tenet of material science is that structure leads to properties. And what better example is that early concept of atomic bonding, leading to this now very fundamental, one of our most fundamental mechanical properties, the elastic modulus or stiffness. So if we go back to that discussion of inter-atomic bonding, we're reminded of how the bonding force curve was the simple first derivative of the bonding energy curve. And we had that neutral axis, which we've circled here. On the force curve, which corresponded to that equilibrium interatomic separation distance, the bond length between any two adjacent atoms. So again, it could be 2 carbon atoms in a polymer. It could be 2 aluminum atoms in an aluminum alloy. Could be distance between aluminum and oxygen ion in the aluminum oxide. In whatever case, that interatomic distance then is going to change slightly in our stress-strain experiment. So when we have this stress-strain tensile test specimen, we're in a position to effectively, down on the atomic scale, we're just trying to pull atoms apart. And of course, in the initial going, we're just simply increasing that bond length by a very small fraction. And so even though this is a highly curved plot, this bonding force curve, again, we emphasized when we're talking about this early on in our discussion of atomic bonding, reviewing those basic chemistry principles that we'd likely seen before, that the tangent at this point is a nearly straight line. So that explains why the overall load elongation curve is straight. Again, it's just a macroscopic scale manifestation of that interatomic bonding, that local atomic structure that we introduced in that very early lesson. And then when we normalize that data, the load versus elongation by sample geometry, then we get the general behavior of the material of stress versus strain. And so then we get this general parameter of the elastic modulus, which again, in terms of just practical mechanical performance of the material, that relates to the stiffness of that component in the overall engineering design.
Okay, so yeah, I need to explain to you this one. So this is the two atoms, yeah, the two atoms, and then this is the bond length. So when we pull this one, kita tarik bebannya, ya. So if we pull this one up and this one down, so what in a very atomic level, the things is the bond also is gonna be stretch, ya, akan tertarik, akan merenggang. Okay, so this metal atom will also increase. That one there. So this one is the, I need to write, this one is between the stress and the strain. So if you remember about modulus elasticity, and then the tangent or the gradient of the between the stress and the strain is called the modulus elasticity or the stiffness. Okay, so that's why metal in this case has a very high modulus elasticity that tells you about the stiffness, kekekaran. So when we increase the load to pull this two specimen, one pulling up and one pulling down, the strain or the kerenggangan, yeah, this would be very low because they have a strong bond. Okay, so that one there. Okay, okay, so that is one videos, and I think I'm missing to, I need to put the other videos about the types of structure summary. I think, yeah, this one. Let's write it. Let's watch it together. So, is it this one or, yeah, this one?
So now let's summarize. We've seen 6 categories of engineered materials today.
Oh, no,
based
sorry,
on...
not this one. Should be the other one. This one.
So for the first of the 10 things that every engineer should know about material science, we're here appropriately enough in the teaching kitchen of the Davis Food Co-op here in Davis, California. And while we're going to spare you our culinary adventure today, we do want to talk about the menu of materials that are available that we should all be familiar with in our everyday life around a kitchen, but also the same menu of materials that are used to produce really all of the engineering systems for modern applications. First of all, a metal pan. We'll see that the first 3 categories that we talk about are informed by the 3 types of primary chemical bonding from freshman chemistry. metallic bonding, those electrons that are providing the glue, holding together individual atomic cores. They define the nature of this material. We recognize this readily as a metal pan. It's a metal pan, first of all, because we can't see through it. Those electrons that are providing the metallic bonding are reflecting any photons, light rays from the environment. It gives us that characteristic shiny luster. Also, the material is electrically conductive. Those bonding electrons are mobile, and therefore think of another common item around any household, any office, of course, is a power cord. And it's the metal that's providing the conductivity and a polymer sheathing that's providing the safety insulation. Well, the second category then we might talk about is the covalent bond. Talked about polymers. Here's the simple polymer or plastic spatula around the kitchen. Very ductile, good structural integrity, but also extremely convenient, lightweight, and so on. That's a case in which the individual atoms, let's say typical hydrocarbon, the carbon atoms and the carbon to hydrogen bonding is covalent in nature. That means that the electrons are being shared between those two adjacent atoms. So in that case, the electrons are spoken for. So again, electrically insulating as opposed to the metal, which is electrically conductive. So the third category would be the ionic bond, which characterizes our third category, the ceramic materials. These ceramics, typical ceramic plate we'd have around the kitchen or the home, common ceramic coffee mug, and so on, would be characteristic of another form of bonding in which the electrons are transferred from a metallic cation to a negative anion, very often oxygen. So this oxide ceramic would be characteristic of the Coulombic forces holding those two charged species, cation and anion, together. Another characteristic of that is, again, the electrons are spoken for, therefore this material is electrically insulating. So three categories: metallic, polymeric, ceramic, based on the three types of chemical bonding: metallic, covalent, and ionic. But I have an additional vessel here. In addition to the ceramic coffee cup, I have a drinking glass, and we, of course, call it a glass. I also call these spectacles I wear around on my head glasses, and these are, of course, optically transparent. This is going to be a fourth category of structural materials, and I included in with the ceramics in a chapter in the associated textbook. In this case, it's optically transparent, again, because of the nature of the ionic bonding, in this case between silicon atoms or silicon ions and oxygen ions, a common silicate material. In mineral form, this could be a silicate ceramic that would go into making the pottery dish. But the key distinction between the ceramic and the glass material, chemically comparable, the same type of ionic bonding, but in the case of the glass, random atomic arrangement of ions in that atomic scale structure. In the ceramic, tends to be a crystalline material with a regular and repeating order to that arrangement. So now we're up to four categories. We have the three basic ones based on the types of bonding, and then an additional subset for glass materials. But let's look at a fifth category of structural materials now, and that would be these small stacking chairs over here, which are familiar to us and have been for the last several decades, since fiberglass was developed after World War II. In this case, we have a material I like to call a structural material that's the best of both worlds. We have the ductility of the polymer, which we saw in that spatula, but it's been given a good deal more structural integrity by the addition of microscopic scale glass fibers, like the glass in that drinking glass, but with a much smaller scale. Again, small fibers, just a few microns in diameter, and that provides a substantially higher strength and stiffness to the material. So again, the best of both worlds, combining the strength and stiffness of the glass reinforcing phase and the ductility of the polymeric matrix. So that gives us 5 structural categories that are adequate for most of our engineering designs, but as a practical matter, we're living in a technological age that's not driven so much by structural considerations, but by the nature of electronic behavior. And so I find it useful to break out a 6th category based on the, if you will, the brain in my laptop here. Of course, we all are dependent upon these machines these days. In this case, it's a very small piece of silicon in which a microscopic scale, in some cases sub-microscopic scale circuit pattern has been printed on that to, again, provide the brain of this device that very often drives our own brain in well-known ways. So again, 6 categories now that we'll use as our menu throughout our understanding and growing understanding of the nature of material science. The 3 categories based on the 3 primary bonding types: metals, polymers, ceramics, and the additional category of glass with the ceramic-like material that is non-crystalline in nature, and then the best of both worlds composite material, the fiberglass, and then finally the semiconductor, in which we have a material in which we can control the conductivity in a very powerful way in microcircuits.
All right. Okay, yeah, that's the 2 videos that we watched. Now, I would like to pause and also ask if you have any questions, please. Anyone?
Excuse me, Miss. For the exam, do we need to remember these materials?
It is open book.
And the characteristics?
Yeah. It is open book. Yeah, of course you have to understand. You have to remember this one, but it is also open book. So you have to have a good strategy, because you can open it on your book, but the time is very limited. So it would be much better if you can understand the concept. Yeah, fun. Okay, is it answering your question?
Yeah, thank you, Miss.
Okay, any other questions? All right, so let's move on. Now let's talk about the crystal structure. Yeah, so we know about the bonding, and then there are yeah, this one, yeah, the bonding for the mixed bonding and so on. And then now let's have a look on the crystal structure. Okay, so in the crystal structure, some of the properties of the solid which depends on the crystal structure of the materials and the manners in which atoms, ions, and molecule are spatially arranged. So usually in the in atomic level there are arrangement ordered, ada aturannya ya. It is ordered, bersusun berulang-ulang, yeah. So that means if a solid has a very good crystal structure which is ordered manners in 3 dimension, we can call the solid is crystalline solid. Okay, so when we describe the crystal structure, I think I have to close my video because my internet is not stable. Okay, so when the crystal structure are described, the atoms or maybe ions, yeah, in the ceramic, we will model that as a solid sphere, seperti bola, yeah. So we call the model is called atomic hard sphere model. Okay, and then one sphere, satu bola, one sphere representing the nearest neighbor atoms touch another. Okay, and then so we can see this one. Yeah, so this is called this one ball. I think I should we will go back in this one in a minute. So this one atom is considered as one ball. Okay, and then because this is for one compound, so the ball all have the similar diameter, and then it is orderly stack, yeah, like that. Okay, go back to here. So and then the crystal lattice, there's a definition of crystal lattice. Okay, the crystal lattice is actually the three-dimension array of points which is coinciding with the atom position or the field center. Okay, and the atomic order in crystalline solids indicates that small groups of atoms will form a repetitive pattern. So then, let's say we have one atom, but then it has a very repetitive pattern. And when we describe it in the crystal structure, then all the repeated entities, we call it the unit cell. Okay, so let's have a look in the next slide. So what is unit cell, and what is the crystal lattice, and then what is the atomic hard sphere model? Okay, so this is how to model or to describe the crystal structure. Okay, so this is just an example. Okay, so the metal, so each metal, they have their own crystal structure. I think I need to write it here. So FCC is stand for face-centered cubic, or in Indonesia we call kubus berpusat muka. So we have a cube, and then in the face, di tiap mukanya, in the center of the face there's also another atom, so it's called a face-centered cubic. Okay, the second one, the category is called BCC, or body centered cubic. In this BCC, they have the atom in the center of the body, or the body centered cubic. And the last one, the most common crystal structure is called the HCP, or hexagonal crossbar. Okay, so this one, the hexagonal crossbar. So for example, the atomic metal, aluminum metal, the crystal structure is FCC, and this is the diameter, and then we can measure it using the maybe TEM, or transmission electron microscope, with a very high magnificence, and then we can find the one atom is about 0.14 of a nanometers, or 10 to the minus 6, or about 1.4 angstrom. Okay, and for example, cadmium is hexagonal close package, or iron, this one, Fa alpha, this is Fa alpha. Alpha means we call it ferrite, because in metals usually they have different phases, fasanya berubah-berubah. So for example, for ferrite, they have a BCC crystal structure, and the atomic diameter is 0.1241. Okay, another one, for example, nickel, that's also FCC, with the diameter is 0.246, or 1.2 angstrom, and then that one there. So this tells you that those metals, they have an ordered positions, with the FCC, PCC, or HCP. Okay, Now, okay, so now let's have a look about the face-centered cubic. So this is the how the face-centered cubic it looks like. So you can have an idea this one. So for example, yeah, this one is the cubic atom. Okay, try to imagine that you have one ball or one atom in all the corner of the cube, okay, and one atom on the center of the face, di muka-mukanya masing-masing. So that's why it's called face-centered cubic or FCC. Okay, if we calculate it or if we make it a very dense atomic cell, it looks like in this one, okay, where you have in each corner if there is a atom, yeah, but because this corner the atom is shared, yeah, between this block and then the upper one and that one and that one and that one. So maybe they have to share this this one, the atom on the corner with maybe about 1 2 3 4 5 6 8 8 cube. Okay, and then here we have also the cube on the face, but then in the picture here there's only there's only half of them, because it's being shared with another cube, yeah, from the front one. Okay, so this is the how we see the cube, yeah, the face centered cube, and this one is the model the arrangement of the atom. So it's basically there is the one that is in the edge, that one, and also on the face. Okay, and if we want to see it on the, if we arrange it like this, it would be looks like this. Okay, now the question is we know the r, we know the radius, yeah, from the previous slides. Okay, now the question is, can I calculate the length of the cube? The questions. Now the approach is so we actually can so this one we modeled them as a cube, for example, there. So the way that we measure the cube length, the first is the dense part. So the dense part would be around this one. So those atoms should touch each other. Okay, if you think about it, the one that is the most dense, where all the balls touch each other, is on the diagonal of the face. Okay, so maybe I can write a diagonal of the face. Okay, that one there. So I know there is one quite large in the middle, maybe like that. Okay, and also there is a quarter around that one in that one there. Okay, yeah, maybe like that, yeah. Okay. So if I think that the cube length is a, okay, and this one is the most dense, yeah, this one is the most dense, the diagonal. So can you calculate how long is the length of the diagonal of this face? So this is r, the radius of the atom, okay, and this is there is a 1 diameter, so there is a 2r, and then there is another r. Okay, so I can conclude that diagonal of face would equal to 4r. Okay, because there is 1r, this is the second one, the diameter 2r, 3r, and this one, the 4r. Okay, now But the diagonal of face, we know if the cube edge length is A, so the diagonal is the, can you calculate how much is the diagonal if the side is A? That became A square root of 2. Remember diagonal sisi? Hello?
Also, it's like Pythagoras gitu, ma'am.
Yeah, because this is A, it is A. Yeah, because this is a square, isn't it? I'm talking about those face. Yeah. Okay, so this is equal to 4r. So with this correlation, I think I can move on to this one. Yeah, so because we know a square root of 2 equal to 4r, then I can calculate a equal to 4r divided by square root of 2, or equal to a 2 square root of 2 of r. Okay, so this actually this one came from, yeah, so in the face-centered cubic, yeah, in a face-centered cubic, if we have if we know the r, which is, we know the radius of the metal, we can calculate the a, or the cube edge length, and then we can learn how much is the volume of 1 cubic cell. Okay, so then for example, I have a question for you in the exam. Okay, so calculate the cube edge length of aluminum, for example. So first you have to check the crystal structure of aluminum. Okay, if it is FCC, then you can apply this one. Okay, so that is the first one, is the cube edge length. The second one, so this is number 1. The second one is the number of atom per unit cell. Yeah, the number of atom per unit cell is defined as the Ni, which is the number of interior atom, jumlah atom yang ada di dalam. Yeah, so we have to write how many atoms that available inside the cube. Okay, it couldn't touch the edge, it couldn't touch the face. Tidak boleh ada di sisi, tidak boleh ada di sudut, harus ada di dalam. Okay, so this is Ni. Okay, and plus with the Nf, which is the number of face atoms. But if you think about it, the face atom we have to divide with 2 because it shares it is like half in 2, yeah, hemisphere. One is for with this one and the one is with the other. Okay, and then the last one is the NC, and for the NC here we have to which is the number of corner atoms in the corner. Okay, if you see here, based on the schematic here, each atom should be divided with 8. Okay, it's 1/8. Okay, so to understand how much number of atom per unit cell, we can apply that into our FCC, that one there, which is Ni, the number of interior atoms so now think about it. Do FCC have the number of interior atoms inside the box? Do we have number atoms inside the box, inside the cube?
No, ma'am.
No, Azra, yeah, because we saw it has some in the edges, yeah, and it has some in the face, but there's no atoms in the middle. Okay, so then that's why we write it 0. Okay, so this is 0. Okay, the second one is Nf, the number of face atom, and then we have to divide it with 2. So how many face that we have in the cube? Berapa sisi ada di dalam kubus? Berapa sisi yang ada di kubus?
6, ma'am.
Yeah, so we have six, yeah. Sorry, we have six. 1, 2, 3, 4, 5, 6. Okay, so you can maybe bring a box or something, and then yeah, you count the sides, and you have six, and then it's divided with 2, so that is become 3. So this is 0, 3, and then we have the edges. There are 8 edges. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, and then divide by 8. So that become 3 plus 1 equal to 4. So that means for FCC, the number of atoms per unit cell, it would be there is a 4. Okay, now and then another parameters in the face-centered cubic is the coordination number. And the coordination number is the number of nearest neighboring or touching atoms. For FCC is about 12. Okay, it's about 12. We have to try to imagine this one. So for example, let me have a look. Yeah, so for example, if this is FCC, okay, and then let's draw with different color. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, and then in the middle, 1, 2, 3, 4, 5, 6, yeah, that one there. So it's a little bit difficult to try to sketch it, yeah, but for one, yeah, for example, for this atom, they will have the neighbor. So we have to consider the neighboring atom, which means semua atom tetangga paling dekat, yeah. So there would be 1, 2, 3. So there would be 1, 2, 3, 4, and 5, something like that, and then 6, and then find another one. So and it would be resulted in FCC, which is 12. Okay. If you still think that still not clear, I think I should let me try to find like an online model where we can try to rotate the model to calculate the FCC. It should be about 12. Okay, and then the last one is the atomic packing factor. The atomic packing factor is the sum of sphere volume. Yeah, the sphere volume of all atoms within the unit cell. So it is actually the I think I should check the atomic packing factor there. Let me open this one. I think I have, maybe I can, oops. Oh, this one, yeah. So it is the atomic packing factor. Okay, so the atomic packing factor is the sum of the sphere volume of all atoms within a unit cell, and then the FCC, the atomic packing factor is called 0.74. So that is the atomic packing factor, and then usually it is it is defined as the volume of the ball, the sphere, divided by the unit cell. So you basically calculate the volume of the sphere and then multiply with 4, because there are 4 atoms in the unit cell, and that is divided by the volume of the unit cell, which is the A, that one there. Okay, so that is about a face-centered cubic. So I think I missed them, so let's put it back where it should go, around this one. Okay. So basically, so there are 1, 2, 3, and 4. Yeah. So there are 4 parameters for one crystal structure. There are cube length. There are number of atom per unit cell. There are coordinate numbers and also the atomic packing factor. Okay, and then let's have a look on the next type of crystal structure. This one is the body-centered cubic. I think this is BCC is much easier to describe compared to FCC. So in a body-centered cubic, you have 8 atoms on the edge and 1 in the middle. Okay, so in order to find the correlation between the cube edge length with the radius, so we have to consider which one is the most dense. And then when we consider the most dense, it's actually the volume diagonal atau diagonal ruang. Okay, so there would be where in this diagonal you can see that the atoms should touch each other. Okay, so let me slice them. Let me slice this one and then put it maybe looks like that. Okay, and we understand this is actually A, which is the cube edge length. This is also the A, but this is going to be the diagonal of the cube, which is A squared 2. Yeah, the Pythagoras that I said. Okay, and then in the diagonal like that, yeah, diagonal ruang, we understand that there would be one large one atom in the middle like that, and also maybe about yeah, the one diameter there and then one diameter there. Okay, and then this is the R. So when we calculate again the cube edge length, so the diagonal is actually equal to a square root of 3. Yeah, the diagonal, that one there, and that should be equal with how many radius? 1R, 2R, 3R, and then 4R. Okay, or maybe yeah, so 1R, 2R, 3R, and 4R. Okay, so then this tells you that the a square root of 3 equal to 4R, and then a would be 4R divided by square root of 3, this one. Yeah, so that is the cube edge. With the similar approach, you can also understand, calculate the number of atom per unit cell, which is the Ni, the one that in the middle. So we have one in the middle, yeah, in the internal one, which is 1. Okay, and then the number on Nf divided by 2, but there is no atom on the face. There is no atom on the face, so we can write it 0. And then we also have the corner. There are 1, 2, 3, 4, 5, 6, 7, 8. 8 divided by 8, so 1 plus 1 equal to 2. So in BCC we have 2 atoms inside the unit cell. Okay, now this is the coordination number is the number of the neighboring atom near one atom. I think this one is better to see, where for example this atom will have 8 neighboring atom. 1, 2, 3. The inside over here is 4, 5, 6, 7, 8. Okay, so this is the coordination number is 8, and the atomic packing factor is the volume of the sphere. Yeah, so yeah, it's the volume of the sphere. So I can write here. So the atomic packing vector is the volume of a sphere divided by cube volume. which is the volume of sphere we have 2, multiply with the volume of sphere would be volume bola ya, 4/3 r f v r power of 3 divided by Q volume would be about 4r div r square root of 3 power of 3. Okay, so then the r can cancel out, and then these numbers will tell you around 0.68. So that means in one packing, in one cube, only 0.68 is accompanied with the metal, while the other 0.32 is the vacancy, kosong. Okay, and this vacancy, ruang kosong, we can later on we can insert another impurities, and we can make alloys. Okay, so that is the body-centered cubic, and the last one, not the last one, yeah, the third one is a simple cubic. In simple cubic, there is none of metallic elements will have this crystal structure. This is because it is too hollow. Yeah, I think the APF is very small. So then if the atomic packing factor is too small, then the atom would seek for a better, higher atomic factor. Okay, terlalu kecil ya atomic packing factornya. So it has a relatively low atomic packing factor except for polonium or metalloid. And then with this one, you can also calculate the cube edge length. For example, if this is the cube edge length A, this is actually looks equal to 2R. Yeah, so you can calculate, if you have a polonium with radius of R, you can calculate the A, and you can calculate the volume of the cube, and then you can also predict how much is the atomic packing factor. All right, maybe I'll stop here, and then let's wait if you have any questions, or give me 1 minute to bring a drink. Okay, any questions? Anyone? All right, let's move on to the next slide then. Oops. Okay. The next one is called Hexagonal Crossbar. In Hexagonal Crossbar, we have N. Yeah. So this looks like this one here. So at the base, you have these 8 balls. Okay, there's sorry, not 8 balls, 6. Yeah, like a hexagonal, and then one in the middle, like that. And then on the top of that, the room between the it's stuck like this one. Yeah, so it's alternate layers. Okay. Another example is when you have maybe this one is much better to see. In the base you have a hexagonal. Okay, you have hexagonal here, so there is 6 atoms in the edges and then 1 in the middle. And then on the second layer you have 1, 2, 3, and then it is continued with 4, 6, 7, 8. So it should be it's actually we actually need to add that one in the other the other cube. That one there, maybe another one the outside, but not in the inside this hexagonal pack. Okay, 1 2 3 4 5 6 7, yeah, something like that. Okay, so it looks like this. So the number of atoms, so here we have A, yeah, and then we have the length of C, and the C is around 1.633 of A, yeah, that is the one, the unit cell. Okay, and the number of atoms in the unit cell is N. So this is the unit cell, the hexagonal prism hexagonal. And then so we have to find how many N, or how many atoms that inside. Yeah, this one, the inside is there are 3 that is inside this prism. 1 2 3. Okay, that one. And then the one that is in the face, divided by 2. So we have the one in the face on the top one, and also from the bottom one, which is 2, divided by 2. And then the one on the corner, so because this is a hexagonal prism, so we have 6 on the bottom, 1 2 3 4 5 6. And then also from the top, 1 2 3 4 5 6. Okay, so then we have 3 in the middle, inside, and then 2 on the face, yeah, divide by 2 become 1, and then 12 on the corner, then divide by 6, this one there, so it's become 2, so then we have 6. So in hexagonal crosspack we have 6 atoms in per unit cell, and then the coordination number is 12. Yeah, for example, this let's have a look on, let's say this atoms, all the neighboring atom of this, the red one, is 1 2 3 4 5 6 on the side, and the top there's 3 1 2 3, so there's a 9. And at the bottom of this red one, there's also 1 2 3, so there would be a 12 coordination number. Yeah, coordination number. So that's the 12 coordination number. And if you have time to calculate the atomic packing factor, you also end up with the atomic packing factor, which is the volume of spheres divided by volume of a unit cell. So you have to calculate the prism, and then this actually would count into 0.74. So it is actually quite large as well. It's quite good atomic packing factor. So we have quite a lot of hexagonal crosspack in many type of metal, because it has a quite high atomic packing factor. Okay, so that's all for the crystal structure. Again, there is the first one is the face center cubic. Yeah, if you go back here, the face center cubic, and the body center cubic, and then the hexagonal crosspack. Yeah, the face center cubic, the body center cubic, and the hexagonal crosspack. All right. Now, any other questions before we move on to the next part?
Ma'am, I have a question, ma'am.
Yeah, okay.
Where do you get is it like from the equation, like you divide it by 2 and divide by 6? Or does it depend on the shape, or?
Which one? This one?
Yeah, like you divide by 6 and divide by 2? Is it like because of the shape is hexagonal? And
Yeah. This one is because the hexagonal. Don't worry. This is so we just follow the formula. So this is the formula, the number of atomic per unit cell for hexagonal crossbar.
thank you, ma'am.
Yeah. Okay. One important things when we calculate the radius, and also we know the radius, yeah, from the atoms also with the cube length, is we can calculate the density, and sometimes the density is actually quite similar with the one that we see on the calculation. Okay, so the knowledge of crystal structure of the metallic solid permits a computation on its theoretical density rho. So the rho or density is actually can be calculated with this formula, which is the number of atom in the per unit cell multiplied with the atomic weight. Okay, and then it's divided with the volume of the unit cell, and then multiply it with the Avogadro's number. And then if we calculate it with this one, I have done calculation before, and also we found it in the book that the density, the theoretical density, is really close with the one that we measure it. Okay, so for a very ideal metal, when we know the crystal structure and we know the volume of the unit cell, then how many atoms associated with each unit cell, we actually can calculate or predict the density. Okay, so after this we're gonna talk about crystal system, but before that, let's watch another video again from the Professor Shackelford. I think there should be another video that we can have a look about the description of those crystals. I think this one. Yeah. Okay, I think it should be just one. Okay, yeah, it should be about crystal here. Okay, so let's watch it together.
And we're here in Kemper Hall on the UC Davis campus, here in the heart of campus, part of the engineering complex. Kemper Hall is named after our second engineering dean, John Dustin Kemper. It's also the home of a number of academic departments, including the Material Science and Engineering program. And we're here today in the Electron Microscope laboratory. Specifically, we'll be learning about the use of the electron microscope to help us understand the nature of point defects and how that leads to solid-state diffusion. The electron microscope behind me is very much like a traditional optical microscope we might be familiar with, perhaps from a high school biology class. In that case, the light microscope is simply a set of glass lenses that refract light in a systematic way to provide a magnified image of some biological sample. In the case of looking at engineering materials on the atomic scale, we use the transmission electron microscope with precisely the same optics, except we have magnetic lenses, electromagnetic lenses that are providing the same function as the glass lenses in the light microscope. And because electrons at high voltage, as they are in the electron microscope, have very short wavelength, we're able to see much higher scale resolutions. We're able to go to the atomic scale, as we'll see, and identify individual atomic arrangements and even individual defects. The title of this segment is Point Defects Explain Solid-State Diffusion. But before we explain what diffusion is and even what point defects are, we should spend a minute talking a bit about crystallography. and simply acknowledging the fact that many of the common materials we use in engineering practice are crystalline in nature, which simply means that on the atomic scale, they have a regular and repeating structure. For example, this stick and ball model here is called a simple cubic crystal structure. It's one in which this cubic arrangement of atoms is representative of the entire material. The small ball here representing the center of an atom at each corner of the crystal. Now, as a practical matter, this is a theoretical structure, not one found in nature for common metals. It's simply too inefficient in the packing. The atomic bonding between actual atoms and the structure, as we talked about in our first segment, prefers a more efficient, higher density packing of the individual atoms. So a better example would be this cubic arrangement in which we have an atom on each corner of a cubic structure, but with additional atoms in the center of each of the cubic faces.
Okay, so
and so we appropriately call this a face-centered cubic crystal structure. This is one which is actually found in many common metal alloys based on aluminum, copper, nickel, and so on. And we'll shortly be going to a set of short lecture segments in which we'll talk about the specific example of aluminum and an alloy in which there are point defects that, again, lead to solid-state diffusion. But the stick and ball model is not a complete story. It's obviously showing where the centers of atoms are. It does show us the overall spatial arrangement of the unit cell nicely, but of course, the balls representing the atoms are much smaller than the atomic spheres would be in reality. So a better model would be this one of atoms full size. This is a case now in which we have our cubic unit cell. And in this, each of the atoms or partial atoms contained within the unit cell are full size. So in this case, they are touching as they would be in the real bonding situation. So again, this represents aluminum. And in this case, this face-centered arrangement, the cubic arrangement on the corners, the face-centered position, all of these atoms are very efficiently packed. And what we see in, if we do a careful audit of the volume of this system, these spheres and spherical segments add up to 74% of the volume of the cube. So again, there's very little empty space or interstitial space between the individual atoms. So now when we begin to talk about defects, we'll see that there are really two types that we can imagine in these otherwise perfect crystal structures. We could simply take one atom away, and that would be a vacancy. Or we can take another atom, let's say another aluminum atom the same size, and, if you will, stuff it into this extra interstitial space. That's going to be difficult, obviously, because, again, there's very little extra space. What we could do, though, is create an interstitial defect with a smaller atom of another type, and that's exactly what happens in common steelmaking processes. We have carbon atoms in an array of iron atoms in that crystallographic structure. So, for example, if we had the face-centered cubic arrangement of iron atoms, as we have in the high-temperature form of iron, a small carbon atom could fit comfortably in this interstitial space, and then its movement around through the crystal structure is the basis of the carbonization of steel. So we'll now go to a video segment which will allow us to understand in more detail what the population of those defects are. We'll specifically focus on vacancies, and then how those vacancies can lead to solid-state diffusion.
All right. Okay, I hope you can understand or have more ideas about the what the model looks like for the vacancy and interstitial maybe later on, yeah, in the next few weeks. Right. Okay, so that is one of the types of the videos tells you about the the atomic models. Yep, sorry. Now, okay, but before we move on to the next part about the defect would be about next week. Before that, we have to learn about the crystal system. Yeah. So once we know the type of the crystals, there are crystal structure. There are BCC, FCC, and HCP. So and then there are so many different possible crystal structure. So it is convenient to divide them into groups according to the unit cell configuration and or atomic arrangement. So we can actually try to make a set of model like this. This is a unit cell, and the unit cell has the lengths, yeah, A, B, and C. It can be similar, like in a cubic crystal structure, or it can be different. Yeah, it can be maybe one is longer. For example, in the hexagonal crossbar, the C is higher compared to A. Okay, and then here also we have the angles. The angles can be 90%, it can be perpendicular to each other, it can be a different, it can be 120 degree, for example. Okay, so the we don't really see it on the metals, but I think this what we saw this on the in minerals in general, in geology or minerals like that. So the cube or cubus, yeah, cube is the has a very large symmetrical degree, and after that is tetragonal, rhombohedral, hexagonal, orthorhombic, monoclinic, and triclinic, something like that. Okay, so let's have a look on the next slides. So this is so we actually name it the crystal system between a cubic up to triclinics, and then this tells you the actual relationship, the length of the A, B, and C, and also the angles, the interaction angles. For example, for the cube, it's a very height ordered, and the actual relationship comprised to A equal to B and C. And the angle, yeah, the angle between the interaxial angle is 90 degrees Celsius. And yeah, 90 degree, not 90 degrees Celsius, okay. And for the hexagonal crossbar, it is written actually like this, the hexagonal, where we have A equal to B, but the C is higher, so it's not equal to C. And the alpha, the angle alpha and angle beta is actually equal to 90 degree, and the angle of gamma is 120 degree. Okay, and then another one, there's a tetragonal where looks like a cube, but the C is higher. And then there is a rhombohedral or trigonal, orthorhombic, monoclinic, and triclinic. I think this one much more found on the minerals compared to common metals. The common metal has the cubic and also hexagonal crystal system. Okay, now there are actually three indicators about the crystallographics. The first one is crystallographic points, the second one is direction, and the last one is about the crystallographic planes. We need to understand, or we should be able to read the crystallographic points, direction, or planes, because that tell you the location or the position. For example, in the previous video, the professor mentioned about defect atau cacat. Yeah. So we can know where is the point of the defect or cacat, yeah, at that time with the position to reference it. Now have a look this one on the first one is the point coordinate. So how you read the point coordinate, we just need to indicate it with the point coordinate with the, for example, with the okay, so for example Q or an S. the QA is the lattice position reference to x-axis. I think it's too small. Yeah, let's make it bigger. Keep. Okay, maybe this one. Yeah. So let's. Okay, so let's consider. Yeah. Maybe this one. Okay, so let's consider. Oops. Let's consider we have a cube. Yeah, we have a cube like this, and then the cube is actually. Can I make a point? Okay, so and this cube, there is the one that this position of P, the position, but I can write or something here, right? So I think I need to still put it. Okay, so I can do that. Okay. So here we have the point of P, yeah. So the position or the way you read the position of P is actually quite similar to the Cartesian coordinate, yeah. So for example, here the point coordinate is the QA is the lattice position of the axis, the reference to the axis. RB is the lattice position reference to the y-axis, and SC is the lattice position references to the z-axis. Okay, so here, for example, can you try to find what is the position here? So the lattice position reference to the x-axis for the QA, because from here to here is 1. Maybe this is around half. Okay, so that would be half. So the position would be the position, for example, here for the point P. Okay. For the point P here would be half. Okay, for the x, and the second one for the RB, the position with the references with the y-axis. So this is y one. This one is 1 scale. So RB is about, let's say RB is a half of the y, so then we can write it a half as well. And the SC, you can see the height. You can compare SC to the C here. So maybe what half. So this point P would be about half. That is the point coordinates. Okay. Maybe let's have a look. How can I will make a mark this one blue. Okay. Can you mention the point coordinate? What is this point coordinate? The blue one. Can you think about the reference position to the x? So you have to project them into the x-axis. So this should be around this area. So that would be equal to 1. Yeah. And then references to y, that would be also, you can project them into the y-axis. So that would also to 1. And when you project it to the z-axis to here, that's also 1. So here the this blue point, the position is 1, 1, 1. Okay. Another example, let's find maybe now it's the green one. How about this one? This point. What is this position reference to the x-axis? Anyone? Aurel, would like to try?
Yes, ma'am.
Yeah. What is the position with respect to x?
I think it's 0 for the x-axis.
This is x-axis. So this is 0. The 0 is just in here, just in the.
Oh yeah, sorry, ma'am.
So around this one. What
that
is
would be 1.
Yeah, that good. So that would be 1. How about the position with respect to y?
That would be
So you project them into the y-axis, which is the y-axis is this one, and then you project them this one. So that would be
0.
yeah, that's good. And how about to the z-axis?
That would also be 0, ma'am.
Okay, so okay, good. So for Aurel said that this position, the green one, is actually 1, 0, 0 because the lattice position to the x is 1, the lattice position to y is 0, and the lattice position to z is 0 as well. Okay, thank you, Aurel. Maybe let's try another one with the red one. Maybe, oh no, maybe the black one. Let's say I have this, I will add this one more, and I will write it in here, this position. Okay, anyone want to try to help me to read it? Lintang, are you there, Lintang? Are you listening? Who want to sekarang tanggal berapa? 19. Okay. Maybe 119. Who has the name 119?
It's V1.
Okay, Sherry. Okay, Sherry. Can you try the position for this black one here? What is the position of the X?
0.
Yep, good. How about the Y?
2.
Right. And how about the Z?
0.
Good. So this is a 0, 2, and 0. Okay, so yeah, so this is like a Cartesian coordinate where we try to make it reference with this one. Okay. Of course, after this, maybe next week, I will give you assignments. But again, the assignments is designed for you to help and to get used to the topics here of the calculation. All right. Okay, so the next one, where is it? I think I have to move this one here. Okay, so that is the point coordinates. The point coordinates tells you the position, and then the way you read it is like reading the 3-dimension of Cartesian. Okay. The second one is the crystallographic direction. Okay, so we know the points, and then we know the direction. In direction, we make a vector. We make a vector, and the vector is, and then we written it as UVW in a square bracket. So we make it this one in a square bracket, which is vector u, vector v, and vector w, where the vector u is defined as the x2 minus x1 of the position, yeah, the final position minus initial position, but in the respect to x, divided with the a is an integer. Okay, a is the length, yeah, the length of the a. And then v is also again with the y, yeah, the final one minus 0 or minus the initial one, but with respect to y, divided by the b. And then z also similar with respect to the z and with respect to c. Okay, and n is the integer. So n is integer, which means we don't, if we have the calculation in the pecahan, yeah, in the, it's not in a round number, we can multiply them with n in order to get the round number. Maybe it's better if I can explain you with this example before. Okay, I think, but it is almost, it's more than 3, yeah, it is should be more than 100 minutes for today, so I think I can explain to you next week about this one. But please do have a look about the problems. I think we can explain this one next week. Okay, so this there would be some example problems, and then also about crystallographic plane as well. Okay, all right. I think it should conclude our lecture for today. So I think so before that, any questions? Who put a check? Okay, Lintang is in the toilet. Okay. Okay. No questions? Right. In some time, I will add more videos about additional course from Coursera. There would be some time for us to, maybe we can play together and we watch together. But if the time is if not enough, you can have look the videos together. Okay, remember 3 credits means around 9 hours to study about engineering materials. Okay, everyone, I think that's all from today from me. Thank you very much for your attention. I will continue this chapter next week on Tuesday. Okay, bye-bye. Thank you.
Thank you.